Hi, this is day 36 and it is brought to you by the entire periodic table. And as you can see today, we have a special guest narrator, T-Rex, and Brontosaurus is supervising the entire production. What we want to do today is just take a quick look at a mass spectrograph. And as you can see, a mass spectrograph, what it does, it finds the mass of atomic nuclei. If you've ever looked at a chemistry textbook and seen a periodic table, there are tons of atomic masses on any periodic table, and they got there because a bunch of physicists figured them out. It's kind of a symbiotic relationship. Physicists figure out the atomic mass for chemists, and chemists, well, they supply us physicists with all the batteries we need, all the potential differences we need for some of the stuff we do. Now, one question you might have is, why do they call this device a mass spectrograph? What exactly does a spectrum have to do with atomic masses? Well, think about what you know about different elements. In any given element, all the atoms have the same number of protons, but some of the atoms will have different numbers of neutrons. Those are isotopes, right? So because the atoms in a given element have different numbers of neutrons, the atoms in a given element, they will have an entire spectrum, an entire range of atomic masses. So that's why this device is called a mass spectrograph. And how does it work? Well, you start off by taking whatever element you're studying and converting it to a gas state and jamming it inside here, and then heating this chamber up like crazy. And when all the atoms, when they're subjected to a really high heat, their electrons get stripped away and you're left with a bunch of positive ions. You're basically just left with the atomic nuclei, which of course are positively charged, and these things are at high temperature, so they're bouncing around like crazy, and some of them bounce out of this little hole and they bounce right into our favorite piece of electrical apparatus, a pair of large oppositely charged plates, positive here, negative here, and the big potential difference between the plates, well, it takes these positive ions and accelerates them across. And they have a tendency to kind of go in every which direction, but a lot of them will hit this hole in the negative plate, and once they hit the hole in the negative plate, they are in the region of a magnetic field. That's what these X's represent, a magnetic field going into the page. And of course, moving charge inside a magnetic field, right away it starts to turn a circle. And some of the ions are going to turn tight circles, some of them not so tight. They're all going to wind up hitting this plate here, which is a detection plate. It records where their impacts take place, and the location of the impact would allow whoever is running this apparatus to measure the radius of curvature of these paths. And of course, using a calculation very similar to what we were doing last time, the mass of these ions, the atomic mass, they can be calculated from the radius of curvature of these paths. Now obviously, bigger mass is going to be less affected by the magnetic force. So instead of turning a really tight circle, a bigger mass will turn a bigger circle. And yes, that is a mass spectrograph. That is how all those atomic nuclei inside your periodic tables, inside your chemistry book, get figured out. There is no assignment to go with this. Very shortly, we will be posting your review sheet for this unit, and we'll also post another couple of videos which are just some demonstrations related to this unit. Your test is going to be posted on Wednesday and due Thursday at 4 p.m. check the written directions and posts on the Google Classroom for more details. Bye for now.